we know the mean of a binomial distribution, which is n times p. And we derived it last time using a formula for the distribution and the formula for the expectation. And we finally arrived at n times p, but it took a long time to get there. Agreed? Because we had to use factorials, we had to simplify, rewrite, a whole lot of stuff. Do I really want to do that with variance also? No, I mean, sure, I can try and get it, but I don't want to. There has to be an easier way. So, suppose y is binomial n comma p, then y can be expressed as a sum of blank random variables. Fill in the blank. That is correct, certainly. But what kind of discrete variable?
I don't know. Discrete is not really
Oh, that is correct. So it is the sum of Bernoulli P random variables. Of course, they have to be independent. So independent. Bernoulli trials are independent by default. So it's Bernoulli P. So I could write y as sum I equals 1 xi, but xi is Bernoulli P. I want to know what the upper limit is. N, very good. So we need n independent Bernoulli trials or n Bernoulli trials. So in order to get n here, I must sum n of them that are Bernoulli. We know the PMF of a Bernoulli, probability of x is equal to, or xi equals 1 is P, and probability of xi equals 0 is 1 minus P. Good. So that's Bernoulli, and I want you to find expectation of xi. Now, we know that anytime we have a binomial experiment, the trials are independent, and every single trial is the same. It's not like I roll a die the first time and then switch over to tossing a coin the second time. Every trial is the same, every success that I've defined is the same. So that has a name. I believe I mentioned it before. No. Starts with the letter I. Has something to do with the 4th of July. Independent and identically distributed. I'll write identically distributed later. So I want you to let me add another part to it, and expectation of y. Xi or I d Bernoulli P, in the sense xi are independent and identically distributed Bernoulli P random variables. So they all behave in the same way. What is the expectation of xi? We have to use the approach that we usually use, sum over all possible outcomes. So in this case, there are only two because xi is Bernoulli. One is 0, the other is 1. K multiplied by probability of x is equal to k. Or to be very specific, xi equals k. So first term 0 multiplied by 1 minus p plus 1 multiplied by p. So 0 plus p, we get p. That is the expected value of a Bernoulli random variable. Now that I know the expected value of a Bernoulli, I could use that information to find the expected value of a binomial. So expectation sum I equals 1 to n xi. By linearity of expectation, what can I do here? What should I be able to do? Move the sum outside. Yes. Good. Now, since I've mentioned that the Bernoullis are independent and identically distributed, every single xi will have the same thing. That's why I had to stress they are identically distributed. So I have p and I am summing n of them. What should I get? MP. Okay, so in order to find the variance of y, we need to find the variance of xi first. Finding the variance of xi is easy. Yes, that we could just use that formula. So we know that value, expectation of xi, which is p. We found it over here, so that part is easy. We just have to find expectation of xi squared, which, using the definition, of expectation, sum over all possible outcomes of the random variable. So in this case, all possible values for Bernoulli, just 2, 0, and 1. K squared times the probability of x equals k, or xi equals k. Yes. When k is 0, you would have 0 squared. Probability xi equals 0 plus 1 squared, probability xi equals 1. Yes? The first term would go away, leaving you with probability of xi is equal to 1, which is simply p. Correct. by definition, that's Bernoulli. So the variance of xi is expectation of x squared, which is p, minus expectation of xi, that is also p, but I'm going to square it. So p squared. So we have p minus p squared. If I pull p out in common, I'll have 1 minus 4. Now we want to find the variance of y. Now, when I went around and some of you did this, which is okay. You can either do expectation of y squared, use the distribution of a binomial struggle. It is going to be real and you'll spend a lot of time. But some of you did this. Yes, this part is easy. Linearity of expectation, pull the sum out, square it, not a big deal. What about that part? Can I simply write this as sum I equals 1 to n xi squared? In other words, can I rewrite this as x1 squared plus x2 squared plus x3 squared? Why not, Andrew?
The sum is squared.
Right, the sum is squared. This is going to be very painful. I don't want to do this because just for 2 random variables, you've got to use FOIL, right? And then 3 of them still FOIL distribute, spend a lot of time. No. This is actually worse than using the PMF directly. So there has to be an easier way. I gave you a hint. The variance of y is equal to the variance of sum I equals 1 to n xi. The very last property of variance that we ended with last time. What does it say? I can pull the sum out under one condition. If they are independent. Which they are, so it checks out. Since that is the case, we can just sum the variances. If they're not independent, then we've got to put in the covariance and it'll get really painful. So I know the variance of Bernoulli, which is p times 1 minus p. I'm summing n of p times 1 minus p. What should I get? N times p times 1 minus p. You know, statistics 2023. You might remember a formula n times p times q. Or n times p times 1 minus p.